In this video, we're just going to have a look at this question. I'm not sure what year it's from, possibly an old mock question. I can't find it in the past papers, so it's more than likely a mock question. But just looking at it there, so it says a modern building which is made from a series of plane surfaces is shown in the image below. Okay, so figure B1 shows the plan and elevation of a model of a similar building. It includes the identical plane surfaces ABC and ABD. Okay, so our ABC and our ABD, they are identical. So this is almost like the spine of our object, and this side are symmetrical. Okay, so they're identical surfaces ABC and ABD. They're identical in size and everything else. Okay, all the lengths of the sides are the same in the whole lot. So the equilateral triangular surface T and the rectangular surface R. Okay, so we can see our rectangular surface R there fairly clearly. It's height 35. That's not going to cause too much hassle. And the equilateral triangular surface T. So surface T there, which we can't see it as a true shape in any view, that is an equilateral triangle if we're looking at that in a true shape. Okay, now we can see that this section here, that's on the ground, which means that this section here, that's obviously a true length, so the length of that is going to be 30. Okay, we can see it there. That's 30, so that's the length of one side of that equilateral triangle. And it obviously runs up along both surfaces then and meets up there at the ridge board. I'm going to call it AB. Okay, so that's that one running up along the surface ABC, and it meets point B up here, and that's its opposite side. And again, I know that the true length of those guys there are 30. So that's 30, and that's going to be 30. Okay, so after that, it gives us again our in, up, down. So that's in from the XY, up from the XY, and down from the XY. Okay, there's our coordinates. Let's draw the plan and elevation of the identical surfaces ABC and ABD. Okay, it doesn't give us a point for D, but I know that it's going to be symmetrical in relation to this object here. Okay, so draw the plan and elevation of those two, determine the dihedral angle between them, and then basically draw in triangle T and rectangle R, and then define a couple of traces. Okay, so I'm going to work through quickly now, just lining out this and basically getting part A done, and then we'll worry about part B. That there now is my ABC lined out, and as I said, ABD is identical to it, so we're basically going to be working across here. We're going to be hinging across this line AB, so we're using that, going straight across it and line out where point D is. So I'm projecting 90 degrees to that line AB, the same distance as it is from C, marking on D and finishing it off. Okay, so that's point D. To bring it up to elevation, finish off the layout of those surfaces there. So bring D straight up onto my elevation. It's on the ground, so CD essentially is a line on the ground. So that's D. Bring it up there, up to point B. Okay, so this is the layout of those objects finished off. Just insert my XY. Okay, heavy it in. So I have my ABC, ABD, inboard plan and elevation. Okay. Okay, so there's both planes lined out there. So now it asks me in part B, so determine the dihedral angle between the two planes. So I need to establish line of intersection. So AB is common to both, so AB is obviously my line of intersection. Normally I would try and take an auxiliary elevation and then come off another plan. In this case, I'm going to actually take an auxiliary plan from my elevation first, just to save me in space. Okay, because looking at the next part of it, I'm going to have to do a little bit of work down here on it. If I take an auxiliary elevation here, it's going to probably overlap more. So I'm going to go on an auxiliary plan and then an auxiliary elevation. And to save myself space, I'm actually going to cut the shape down a little bit. So I'll show you now what I mean by that. So AB being this length here, I'm not going to take the full length of AB. Okay, I'm going to pick a point and say it doesn't really matter whereabouts along it I pick it. I'm going to shorten it slightly just to save me on space over here because I could get caught. So I'm going to pick a point here, say 50 millimeters along that spine, if you like, in plan, along that ridge burden plan from A. Okay, so I'm going to pick that point there, and I'm going to basically cut that off then at that point. So I'm going to project it off the elevation. So that's that point there on elevation. Okay, so basically instead of taking the full length of AB to get true length, I'm just going to take this part here. It's not going to affect the outcome of it at all. Okay, it will mean that I won't have a true representation of the true length of AB, but I'll be able to get the true length of this section, and I'll still be able to work out the dihedral angle between both surfaces, between both planes. Okay, so I'm just going to project across that as well. So now I'm cutting that plane, or I'm cutting the plane that I had. Okay, so I'm cutting it across there, and I'm going to say I'm going to take this point instead, and I'm going to take this point here. So I'm going to call this 1, 2, and the top point of a tree. So almost I'm just slicing it straight down there. Okay, so this is point 3. I want to locate point 1 and 2. So it's a little bit more work setting it up here, but I just want to save myself that little bit of space because I think I could get caught with it. Project that up to the ground. Project point 2 up to the ground. Actually lines up very close to point C. That's just the way it is. That's not intentional. Okay, so basically I have my points 1, 2, and 3 there. Okay, so now I'm going to go ahead and find my auxiliary plan. So working off the elevation. So that is still my line of intersection along that line AB. So I'm going to draw a new XY parallel to it, and then I'm going to project 90 degrees to that. Okay, so point A projected up, and my point 2, my point 3, and my point 1. Okay, that's point 1. So auxiliary plan, take the distance from the vertical plane out to the plan, or from my XY down to my plan. So for point A, well, I know that then because it's given to me in the question as being down 30. So that's 30. That's A. So this time the line of intersection is A3 rather than AB because I've shortened it. Okay. So I'm going to get the distance from 3 now down to line down to the XY, or out from the vertical plane. Same thing, and I'm going to mark that off here. I'm going to do the same for 1 and for 2. So get the distance for 1, mark it off my new view, and get the distance for 2, and mark that off in the new view. So take that distance there for 2, and mark it off up here in the new view. So that's my new plan up there. So that's 3, that's 2, and that's 1. So extend that 1 line to hit it. Okay, so that's point 1. So first of all, my line of intersection, of course, is my line A3. And my two planes are A13, which was my old ABC, and A23, which was my old ABD. Okay, so again, I'm going to colour them in as they were. So A23 is my blue plane, Now I'm just going to take a view now looking along that length. So look along the true length of A3. So looking down along it, and that's going to give me an edge view of both planes, which will give me my dihedral angle between them. Okay, so project everything, looking down along it. Alright now, so A3. Okay, and I want to draw an XY then 90 degrees to that. Okay, so that's my X2, Y2. X2, Y2. This guy here is my X1, Y1. Okay, so just heavy in those. Okay, so this time I take my distance from my X1, Y1 back to my elevation and marking them off here, and I get my plane as an edge view. So A3, of course, as it would be normal, that is the same distance, because our X1, Y1 was parallel to that. So that's the same distance there. That's going to give me points 3 and point A. 3 is first, obviously, because I see it first here. Now I take my distance for point 2. I mark that off in my new view. So from my X2, Y2, mark it off. That's 2, and then I get it for 1. Yes, that's my dihedral sorted. Okay, and again, just label it up as being your dihedral angle between both planes. Okay. So that's my dihedral angle there. Okay, so I just shortened it there to save me a little bit of space, and it worked out fine. Now the next part then, it says complete the elevation and plan by drawing the equilateral triangle T and the rectangle R. So the rectangle R is nice and handy. I'm just going to mark that in there now. You can see it's at a height of 35, cuts through CB here, and then where it meets line BD, it drops straight down, and it's going to give me those 2 points there. Okay, so that's looking down in the plan. It appears there's my single line. Okay, so that's my rectangle R marked in there. Now I want to work on my equilateral triangle down along here somewhere. So it does give me the length of the side that has been 30. So what I'm going to do is I'm just going to mark out 15 either side of my ridge border or my spine. I'm going to go 15 here. I'm going to go 15 here. That'll give me my 30. I'm just going to project that up then to where it would be. Okay, so here to here, and it should be parallel with this line also. And it is spot on, that's grand. Okay, I can project that now up to my elevation. Okay, so I'm going to call this 0.4 and 0.5, and the top of it I'm going to call 0.6 when I find out where that is. That's 5 and that's 4 up there. Now, in order to find the top of that, I kind of need to look at the plane ABC being flat, okay, because it shows me in the question, okay, the edge of that runs right up along that surface. So that's a 30mm line running along that surface there, and we can see it as well in plan. 30mm line running along that surface. That's a 30mm line going along the ground. 30mm line running along this surface here, and that gives our equilateral triangle. Okay, and in plan, or in elevation rather, we can see that that's the angle it has to make. It has to hit the roof of it there, so it fits in. So we imagine that being on the ground, it swings up, and bang, it gets stuck at that point there. Okay, so I'm going to go now and look at that. The handiest way to do that is if we were to take that edge A, or that surface ABC, okay, and if we were to stick a hinge on it here, stick a hinge on it here, so there are two hinges, and then we're going to, for all the world, we're going to fold that over. Okay, so on that line AC, fold over that surface. So we'll say AB, which is a true length, to be down here somewhere, and AC then the true length there. And then we're going to get, if we had a 30mm triangle on its back first, and then if we swing it up into position, it'll give us the position where it hits. It'll give us this point here, and we just project that back along, project that back up the elevation. Okay? So looking at what I've done there now, so that is the line that I want to hinge over, the line there AC. I can hinge over this line because it's a true length line. It's on the ground for me already. I can see that in elevation AC. That's on the ground. It's a true length line, so I can rabat over it. I can hinge over it. Okay? And I need to find the true length then of the other ones. Okay, I need to find the true length of AB. I need to find the true length of CB. And that's easy enough to do. Now, at the very start, if I had taken the full true length of AB from my line of section, that step would be done for me now, and I could just mark it off. But it's not the end of the world. It's not too hard to find. So what I'm going to do there, I'm actually just going to use the same section that I used for my auxiliary plan up here. So I'm still going to use this 0.3 here because I have the true length of that. Okay, it doesn't matter if I don't flip over the whole triangle, as long as I flip over the section that contains the equilateral triangle, and if I flip it over as far as here, that's going to allow me to do that. Okay, the whole one might not fit either. Okay, so I'm going to take that length of A3, so I'm going to take that true length of A3, okay, and I'm going to swing it here. Okay, because this is the true length, and now that's the true length of A3 all the way along that arc. And now I want to find the true length of the next one. So we have the true length of A3, swung it over, found it there. We have the true length already of that there, and now I want to find the true length almost from here up to 0.3. Okay, so 0.1 kind of up to 0.3, so I'm using that instead, and I'm going to swing that over. Okay, so in order to find the true length of that, I want to make that horizontal here in plan, and then look at it in elevation. Okay, so I want to take that 0.3, 3.1. I want to swing that around, so I'm rabatting that around. We've done this before. 3 stays where it is. 1 is being rotated until it's a horizontal line of plan. So project this up. Now because it's horizontal here, when I redo it up here, it's going to give me my true length. Okay, so 1 was on the ground, it's going to stay on the ground, but it's going to come out as far as here. 3 stays where it is, up here. And that now is going to give me that true length there of 1, 3. Okay, so that now is my true length that I can now use. So set my compass to that distance there. Right, so I'm going to just mark it then from here out, and where it cuts over, that's going to give me my 0.3. So I'll mark it from 0.1, where it crosses that one there, that gives me 3. And then I can join that back up again there. Okay, so as I said, we hinge completely on this line here, just fold out, flatten that line. I could have taken the full object there, the full plane ABC, and rotated the whole thing around, but I didn't have the length of AB. Now I could have found it the very same way as I done this one. Okay, but I already had A3 here, and that was enough because it fit in the portion of the drawing that I want. So there was no need to go and do the rest of it. Okay, so what I want to do there now is from this point here, I know that's a point on the ground where my equilateral triangle is, and we've already said I want to swing an arc of 30 from there. That's 30. So if we can imagine that equilateral triangle line flat on the ground, and then we swing it up. Okay, so swinging back here, and it cuts right there. So what that's going to give me is one of my sides of my equilateral triangle. Okay, if we look at the drawing again, the question, it's going to give me that line there, okay, when that triangle is folded out flat. And now I have my apex points, that's 4, 5, I said this is going to be 6, so that's going to give me 0.6. I can now project that back down and back up to my elevation. And again, everything is being projected 90 degrees to my hinge line, of course, which is this line here, AC. So everything is going 90 degrees to that. So there, just move some equipment out of the way. So I can project back 0.6. Okay, and I get that point there now where it actually cuts the spine of my object. You can see in the question there, solid lines. There are visible lines on that surface. Now I just project that up to my elevation, and it gives me its location. So it's 5, what's that guy? It says a solid line, and the one from 4 is a dotted line. Okay, so that's the equilateral triangle now drawn inside that view there. Right, so the next part of the question, determine and indicate the horizontal and vertical traces of the oblique plane for the surface BCD. Okay, so my surface BCD, so this guy here at the front. Okay, so BCD, so if we can imagine that front surface there, so they want me to do the horizontal and vertical traces for that surface. Now, so horizontal trace first, so that's a line obviously we know that's on the ground. CD is already on the ground, so that is obviously part of my horizontal trace. So that's my horizontal trace. Vertical trace, if I take a horizontal cut to the highest point in the object, it can be any point, but the highest point is the best one. The points are furthest apart is a more accurate line. Extend it till I hit my vertical plane. In plan, which is my XY line, bring it up to elevation. So that horizontal cut here is a horizontal cut as well, which is a straight line in elevation. Okay, that's going to give me my VTH, my vertical trace. Okay.